Okay, so good afternoon for everyone. So I will be presenting about how optimize global time series machine learning predictions. So from modeling to production deployment. And yeah, it's the last session, not the last one of the last sessions in the last day. So I hope I'm able to keep the interest of you. And I think it was a very nice workshop hackathon. We did a lot of hands-on work, and the idea here of my presentation it's explain how we implemented some of the pipelines that we discussed here internal at OpenGeoHub, and basically share some of the lessons learned that we have. Let me pass here. Okay, so I will basically the work that I'm presenting here. It's in the context of the Global Pasture Watch Initiative, and this initiative it's basically a consortium that it's monitoring grassland and livestock in the world. So OpenGeoHub, it's part of it. IASA, Federal University of Goiás in Brazil, the IDIV, Cornell University, and also the GLAD, the University of Maryland. And the work is supported and funded by the Land and Carbon Lab and WRI, and it's under the initiative of the Bezos Earth Fund. So in this project, mainly we are producing 4 mapping products. So the Land and Carbon Initiative, it's working with a baseline of 2000, the year 2000, and they are doing most of the mapping products at 30 meter. So 2000, 30 meter of spatial resolution. It implies the usage of the Landsat data. And in the project, we are mapping mainly 4 categories, 4 products we are deriving. So the grassland dynamic maps, the livestock density maps, short vegetation height maps that is using the data presented by UFON yesterday, and the GPP, the gross primary productivity. All these 4 products, they are relying on the Landsat data that Tom also presented in his presentation, and I will focus here in the grass dynamics maps. So how we produce it and operationalize it in practice. Basically, we have this fancy workflow that we just submitted now the publication, so it's in peer review. We also have the research, the preprint in the research square. But yeah, this is all the steps. I will not focus in most of the steps here, but if you just get this whole pipeline, you can mostly simplify it like that. So basically, we have petabytes of Earth observation data. We have some reference points. In this case, it's also a million of points. And basically, we do this space-time overlay, the extract operation. So basically, for every point, we want to extract the raster pixels. We produce some tabular representation of that when you do any machine learning model, conventional machine learning model as random forest, SVM, you mostly have this spreadsheet, this table with the data. So we apply some machine learning workflow and we end up with a model, right? And this model can be a random forest. This is actually like an artifact. It's like a model that we trained that it's able to predict one of the targets. So in this case, the target is grassland. But if you are mapping land cover, the target it's different land cover types. If you are mapping soil organic carbon, the target is the quantity, how much soil organic carbon you have in the soil, for example, in different points. But in Earth observation data, mainly we want to use the model to do predictions. That's actually the main aim here. And to do it in an operational way, you really need to have ways to scale up the computation, right? So the last step, this machine learning prediction, is where I will focus here in my presentation. So you can train the model, you have it, but now how you apply it in petabytes of data, how you apply it in a per pixel, 30 meter, 23 years. That's the main point here. So, we produced the maps. So this is an example of basically we have 2 types of grassland, cultivated grassland and natural and semi-natural. This is the probability of these two classes. So it's actually, it's at global scale, it's the first product that it's mapping two types of grassland. And if you combine them, you end up with these two types of grassland worldwide at 30 meters. And of course, you can do some temporal analysis. And here is an example in Paraguay, how you can see the expansion of the cultivated grassland over the natural vegetation. And this data, it's 30 meters. So, and basically we had to really think how we could do it. So, and you can access the preprint here. The maps, we uploaded some maps to the Google Earth engine, but we will make everything available as a stack, right? So this is, again, just an introduction to the problem and to the talk. But what I really want to show to you is how we actually produced those maps, right? How we went to like a machine learning model that we trained to predict like millions and millions of pixels. So, and basically the first step, several presentations explained it. We also saw it with our OpenGeo colleagues. So specifically for this problem, we split the world in tiles, multiple tiles. And in our case, we actually materialize the tiles. The tiles are basically a geopackage file where you can see here's a tile and here's ID, right? And you can see that the tile, it's not completely regular. It's a grid, of course, it's a grid, but we removed all the tiles that has no data. We don't want to have tiles in the ocean, right? But once you have, like, depending on the way that the data is structured, you might have some data there, but you don't need to load that. This would be basically slow down the total computation time. So basically, that's the number of tiles that we have. So 18,607 tiles. And each of these tiles, it's about 4,000 by 4,000 pixels. It's 4,004 because there's a small overlap among them. So, and what we do with these tiles is basically, we want to load a lot of data and apply a machine learning on it. And the model, it's already trained. I will show it in the next slide. But here's an example of a tile that it's covering Vienna, right? And Tom presented also in his presentation, but the data that we are using, it's mostly Landsat. We have some static data also, but here you can see how the data looks like. This is 2022. So we have every 2 months a composite and gap-free, right? We basically did a lot of pre-processing in this data. And this data, it's not a kind of a regular Landsat collection. This data was produced by the University of Maryland that has a direct link with the USGIS, and they invested years of research to harmonize all the Landsat satellites, all the Landsat systems. So it's basically Landsat 5, 7, 8, and 9 together, but with reflectance cross-calibrated. What it means that I can have a model that I train, for example, in the most recent years, where I mostly probably have more samples, and I can apply in the past, because the values of the pixels, of the Landsat pixels, they are cross-calibrated among the whole time series. So we have another paper explaining it, so I will not focus on it. But it's important to understand here, this data, it's already pre-processed. We save it in our system, and we did that for the whole world. And here it's a kind of a general pipeline where we took this harmonized data, we removed clouds, we aggregated for every 2 months, and we did a kind of a time series reconstruction algorithm that worked in time and basically fill all the gaps, considering some observation in time for that pixel. We don't rely in this spatial gap filling, and we saw some examples here because depending on the application, it's close to magic, right? So, and in this case, we prefer to gap fill with some pixel that at least it's from that area, but from a different period. So, and for the application here, it makes more sense. So, okay, but how this data looks like, right? Here, I'm just showing the INIR, but we have 7 bands. So we have blue, green, red, INIR, SWOR1, SWOR2, and thermal band. And for every band, we have 6 dates. So it's a kind of the same dates that I'm showing here, but for all the bands, right? But on top of that, you can also put indices. So we can have NDVI, EVI, NDWI, tillage index, FAPAR. So there is like even there's a new paper about it, and like you can find like this. I don't know the name by heart, but there is a GitHub a link with a lot of these indices. Like you can really derive multiple indices, and awesome spectral indices. And here we derived 7 indices. So, okay, so 7 indices, 7 bands, 6 dates. But we have 23 years of data and for all of it, and 16 million pixels per tile, right? So we really need to read this data, organize in a way that we will send it to the machine learning algorithm. And the idea to optimize here is we will predict all the years at once. So we minimize the overhead and the changing context. So we read all the data that it's necessary to predict one tile, and we will just predict it with the classical machine learning algorithm. In this case, it's the random forest algorithm. But the data that I show, it was basically temporal data, right? It's yearly. Every year we have that same stack of data. And also our models combine also static layers. Because, for example, we have DTM only for a few periods or maybe 1 or 2 years. But we also want to use this DTM in the algorithm. So we have also what we call here static layers. And for the static layers, we also have distance maps, some long-term water vapor, long-term daytime temperature. So when I mean long-term, it's basically what is the average daytime temperature of January, for example. And if you combine all these static layers, it's about 85 static layers. So we also need to read that and put in a way that it will be able to run predictions with like a regular method of, for example, scikit-learn. Okay, there is one trick that it's important to explain is some of this data that I presented here, they are actually 1 kilometer. And if you just put this 1 kilometer data in your predictions, you will mostly see these blocking effects, right? You can clearly see the pixel of 1 kilometer. So to combine this data, we basically use this downscale trick that here as you can see the line. So basically we get this TIFF file. This is 1 kilometer data. And we apply a cubic spline algorithm, change the pixel size, and derive a VRT. Once we do it, we learned about VRT in the first day, right? But once we do it, if I read this data with QuantGIS or with Raster.io or R, the GDAL will be in charge to do this reprojection on the fly. And I can literally have the data like that. And I don't know if it's possible to see. Yeah. So it's like this, and you basically smooth this blocking effect. It's a way to remove this blocking effect. And so in the predictions, you can still see these patterns, right? There's no magic. The data, it's still 1 kilometer. But here we are really kind of smoothing this pretty regular pixels to match with something that will probably fits better, for example, with the landscape and with the predictions, if correlates with the target variable, right? Okay, so basically how we are doing it. So the first step is we load all the static layers. It's 85 here, yeah, it's 88 static layers. We load all the temporal layers, the Landsat bands, all the years. And the on-the-fly layers, it's basically the indices. So we don't have, for example, NDVI and all the indices calculated, because otherwise we need to calculate and save in our storage system. And that will take time to calculate and time to read and load. And here you can see an animation of our system reading this data. So basically here, we have CPU servers accessing the storage servers. And basically you can see the first information that you see here in this plot, it's the static layer. And the second information in the second jump here, it's reading in about 700 megabits, right, per second. So, and you can see the time to read all this information. So once we did that, we can now load this data. This is occupy a continuous space in RAM, and it's about 70 gigabytes of RAM. But for the on-the-fly layers, we still need to compute NDVI, we still need to compute NDTI and several other indices because we need to have it for the modeling, but we don't save it, so we compute it on the fly. So, and to do this computation on the fly, there are some options. So here it's a course that it's more like a 1 hour workshop where I mostly explain how to use these 3 libraries. So here you have this bottleneck, NumPy, NumExpr, I never say the right way to say it. I never know the right way to say it, and Numba. And basically with these 3 operations, you can really speed up any NumPy calculation. And just to give a glance, you can see here, for example, 3 code snippets, how to use it. So with bottleneck, it's drop-in replacement. You can just calculate this NAA median. It's the same signature. You just replace the import, and you have like a speed up here, for example, I don't know, 6 times, right? And if you compare with Numba, the same operation, I checked it numerically. I show how to do in the course. It's exactly the same output, but you speed up because these libraries, they implement some of the core calculations in C and also in just in-time compilation. So you can use that to optimize. But even doing it, it was not enough. So we also pushed it a bit more, and we implemented the calculation. So you can see how we computed the NDVI, and here it's the C++ code. It's basically relying this framework, this Eigen. I don't have much experience with that, but it's a kind of a linear algebra and matrix vector numerical. So it's pretty close to NumPy for C++. And OpenP to do the parallelization. And with that, we got like a speed up of 6 times. So every step that I'm showing to you, it makes difference. And it was something that we were developing and testing to really manage to speed up the prediction and be able to run all the maps in a reasonable time. Okay, once we have this data, it's coming, yeah. Once we have this data loaded, this is a nice format, but this is not what a machine learning algorithm in scikit-learn, for example, expect for predict. So because the data needs to be organized in a transposed way. So you can literally see how many pixels we have in the top, how many variables we have, features, and we want to predict all the years at once. So here what we did, we basically replicated the static layers for every year. We organized the temporal layers in this continuous way also, and we transpose also the on-the-fly layers. So this operation also takes time, about 20, 30 seconds, and occupies, of course, more RAM. And here we are talking about like 500 gigs of RAM. And you can see here, it's 1 terabyte of RAM that we have in these servers. And here it's only showing half of the cores. You also have more 48. And
Leandro, is this gigabit or gigabyte?
Sorry?
Gigabit or gigabyte?
Gigabyte. Gigabyte. Yeah. Oh, okay. So yeah, and you can see here, if you just divide this number by 23, we literally have the same number of pixels here. So it's basically a data transposition that it's putting all the pixels that I want to predict in a way that the machine learning algorithm will understand. But there is also another thing. So here it's a tile covering the Amazon region, and I just took this tile because it's better to explain. We don't need to predict water, for example, or all the pixels of like continuous forest. Even that we are looking grassland, we can still select and create what we are calling here some prediction mask. And of course, you can run the prediction for all over the world. The best, for example, if you would have like a more conservative approach, you just remove water. But here also, we used some existing product produced by University of Maryland, and we excluded all the pixels that appear in these classes here during all the years. So if there was a pixel that was mapped as forest between 2000 and 2020, in all the maps, we excluded. But if it appeared at least one year in this whole time series, we kept it. So this removed a lot of the areas. And also, of course, if you don't want to predict that, it will speed up because we don't need to propagate this pixel among the random forest algorithm. So that's also another trick that we did. And again, if we would be, okay, now that we speed up, we could still predict for the whole land mask, but for water in this case, it's nonsensical. So we really need to remove water. Okay, doing that, there is another step that it's actually we implemented together with this data transpose to apply the prediction mask. And now we reduce a bit the number of pixels. And with that, we are literally ready to do the predict. So it's literally doing, right? We have model, we loaded. This is a random forest model. We can predict, or we can run predict proba to generate probabilities. And in specific, in this case, we have two models. So we have one model to map cultivated grassland and one model to map natural and semi-natural grassland. So, and all these operations that I said to you, we need to load the data, we need to apply a mask, we need to transpose. So after that, we are ready to run the machine learning model. And here, we trained these models basically with the same input features. So we can take advantage of all these operations that happen. So once the data is ready, I can literally run the predict for the two machine learning models and take advantage of these common operations. So, and we basically create a union of features that was important for that were important for the both models. Okay, it's okay. We could, I'm using here scikit-learn, but you can use XGBoost, CatBoost, scikeras, MAPI. So all these libraries, they are pretty compatible with this interface of the scikit-learn. This is a very nice advantage of Python. And also you can find tons of algorithms in this awesome Python data science. And you can run, and once you run this model, you will have like the same number of pixels, but now with the probabilities of cultivated grass and the probabilities of natural or semi-natural grass. So basically you are interpreting all the features and creating this probability grassland. But if you run this with the scikit-learn model, it takes about exactly this number of pixels, it takes about 800 seconds. And it's still good. But when we did this calculation, it was something about 2 or 3 weeks to do the maps for the whole world. And we started talking, okay, how we can optimize it. And I discovered this framework that it's pretty nice, called Hummingbird. And Hummingbird, it's basically a library for compile trained traditional machine learning models in tensor computation. So, okay, that's perfect. Let's use it. And how we can use it? Basically, Hummingbird convert your scikit-learn model or your XGBoost model for ONX, TVM. I didn't use TVM before, but it's like a Apache initiative or for a tensor torch script actually to be better. So, okay, it's basically a parser that's perfect. And I started digging. We have CPU processors, CPU servers. And okay, the best is actually use this TVM. This is suitable for CPU inference. And let's try to convert the random forest that we produced for this representation. It doesn't work. So I tried for days, and why it doesn't work? I tested with some toy example and it worked, but there is a catch. These two models, they are production models. It means that the tree here, they are quite deep, and you have several nodes, right? So every model that we have here, they have 60 trees. Every tree has an average depth of 33 depths. The natural and semi-natural grass is 40 depths, and you have like thousands of nodes. So once you try to convert it, use the library, it simply doesn't work because this is a production model, right? It's a model that tries to really tackle like a real problem. It's not something that you did with some benchmark data set. Okay, so, okay, what are the other options that we can do? So when I managed to find this thing, and this is really nice. So this is exactly what we were looking for. It's a model compiler for decision tree models. And this is a pretty old technique. If you go here, like it's a blog from 10 years ago, they literally convert a tree representation in a C code. And you can see the code here. So every if else, it's a decision path in a decision node in the random forest. And you have literally 60 source files. And here is a pure C code, right? You can see the if else, what will happen when achieved here, what is the probability. So this is actually what it's inside of a random forest algorithm when you train it. So this framework, TL2CGen, I remember we cited it in the paper, in the publication. I remember the PanGeo colleagues saying that we should cite the package, and we cited because, to be honest, they are pretty unknown, the framework, but it's very nice developed. So once you have these files, you can compile with GCC or an Intel compiler. And we compiled with an Intel compiler, and we managed to speed up it 80 times. And because this use this weird representation in the input, you need to create some intermediate representation, what they call D matrix. But the prediction time with the compiled model, it's really fast. So, and okay, now it's pretty good. We are happy with that. So, and once we did that, okay, now we have the data in that format. We need to do this probability output. So basically, we need to kind of back transpose the data. And here are the maps that we produced. Again, this, I don't know if you just remember, in the beginning, this is for one tile. So everything that we presented here, it's one tile. So, and we tested it, of course, with one tile. And when we were quite happy, okay, now it's ready to go to the production, we can scale up and really send it for all our servers. And basically how we did that, it's literally using the same thing that we learned here. It's coming, basically using a slurp. So we have a job ID, and we know the total number of tiles, and we just split a chunk of tiles for every server. So it's basically using the same structure that Giuseppe presented. And here you can see we have we used 12 CPU servers with exactly this configuration, 96 threads, 1 terabyte of RAM. And we just split and we send the chunk of tiles. And inside of every CPU, we created a Docker. With this Docker, we start up the script. And the script just iterate over all the tiles, reading the data, and doing all the operations that I presented here. And we also use an object storage solution internally. We are relying on the COE, the FS. So it's also support the S3 protocol. And one thing that makes like a lot of difference, as I show in the animation, is the infinite band. So we can really move the data quite fast. And now actually the bottleneck in our case, it's literally the disk speed. And once we have the tiles processed, we put it back in the S3, and we do a GDAL build VRT and a GDAL translate to produce back the maps. So in the end, we have the tiles, we produce all the tiles, but we need to merge it back and create like a big mosaic, as I show in the beginning of the presentation. And once we do it, the job is finished, right? So, and basically we prepared everything as COG, and we put in a public URL, and people can just use the data as it goes. So if you think about it, it's basically, we also learned it with Raymond, it's basically this, it's nearly embarrassingly parallel, because you still need to have some level of control in the beginning and in the end. Right? You still need to define the tiles, how you split the tiles, you send it, you run everything in parallel, and you need to aggregate the result back because people want to see the whole map. Even when we were checking the results during the computation, we are anxious to really see the whole prediction, because once you see the whole map, you can understand better the problems. So these two steps in the beginning and the end, they are really important for massive predictions, as I'm showing here. And here is literally how we did it in the Slurm. So basically, we create this submit job. So this is just a shell script file. You can see in the top here the number of the job array that we use. we exclude some servers. We have 14 servers, so we keep like some reasonable names for them, like Atlas, Europa, Bender, so kind of diverse. But we use these names because it's still only 14 servers, so we can still manage. So here we define the number of tiles that we use, the Docker image that we want to run, the language. This is just some variables that I created, and I call execute. Once I do it, there is like a set of functions that I created that will instantiate a Docker container, attach it with the operation system. So if you kill the Slurm, you basically killed also the Docker, and you have inside of the container, for every CPU inside of the container, you have a bash script where you can do some kind of general configurations. And here we are setting up some of the parameters that we use. And here it's basically the run py script. And in this case, every script receives 3 parameters. So the initial and the final range of the tiles, the server name, so to do some operation locally. And with that, we parallelize internally, right? So in this case, it's kind of optional because all the steps that I show here, the setup of the container, everything, it will happen only once. And inside of the container, we iterate tile by tile. So for example, if I need to load the model, I only load once and I do all the operations that I need to do. So the only thing that I really need to do, all the operations that I really need to do per tile, it's really reading and prediction. But some of those operations I can just do once and I don't lose the context in the execution. Okay, so main takeaways. This pipeline that I presented here, it's complex, and I have to say it's also difficult to maintain. Not the Slurm part, but all this transpose. But on the other hand, it reduced the production time for 40 days to 7 days, and that's a huge difference for us. So, and now what we are doing is several of the functions that I show, we actually implemented them in C and C++. So to kind of bypass the GIL, the global interpreter lock of Python, and take advantage of multi-processing, multi-threading actually in C++. And we are now encapsulating it and putting this package called scikit-map. So there's still a lot of work, but we are organizing it in a way that people can really reuse it in different pipelines. So maybe you really don't need such complex pipeline. We really did that because we are working with Landsat data whole world. But you can still take some of the things that I show here, like parallel reading, on-the-fly calculation, the use of the third-party libraries, and use it in your application, right? And also the full reproducibility of this pipeline really depends on the input and Earth observation data. It needs to be public accessible, right? We run it in our infrastructure. So also the container needs to have all the libraries, everything needs to be organized, and also we need to have better code abstraction. So that's exactly what we are doing now. So, and this amount of data that we kind of streamed through this pipeline, it was about 400 terabytes because this was already the gap-filled Landsat. So, and if you think about it, maybe we will not have like these 400 terabytes available at some place. We are trying to do it and hosting somewhere, but at least we can prepare a few tiles so people can reproduce all these steps with some kind of a sample data set that at least resembles the whole pipeline. And yeah, so basically here I finished my presentation, and thank you for the attention.
Yeah, Leandro, SchemApp is already ready to go for operation or need some improvement?
No, now it's ready to go for operation. So you mean that the Slurm part? The Slurm part that I show, we really use to different stuff to produce cogs and things like that. But the machine learning pipeline, it's ready to go. What we are trying to do now is all this transposition and all this parallel reading, we implemented a lot of stuff in C++, and now we are moving it to the scikit map with this PyBind abstraction, so to communicate it, because we have like the Python interface there, but it's still several functions. We need to have a better abstractions to make it to use. But now, for example, we are waiting for the revision, and we will for sure produce one more time of the maps, and it's ready to go.
You done this up? Wait, nice to see all this stuff. Also nice to see you're moving to C++ for good reasons. Question on the data logistics. So just comment, I mean, from a pure computer perspective, it's fully embarrassingly parallel. I mean, the aggregation at the end is considered to make it less embarrassing. But you're using an almost HPC way to do the traditional HPC way to do the data logistics. So InfiniBand, putting a shared FS in front of a box storage store type solution, which is quite heterogeneous. So can you say a little bit more about it as to why those choices were made? Because don't see those choices very often.
Yeah, okay. Thank you for the question. So the first thing is we before this pipeline, this is the application, right? We also we gap filled this Landsat data, and this was a bit more heavily data-wise because the data that we got, the Landsat R&D, it's about 1.3 petabytes, and we just converted it for about 400 terabytes. So we gap filled and we did this aggregation. But in the end, you really need to stream 1.3 petabytes. And we have basically data storage and CPU servers. So we moved it to the InfiniBand just because otherwise wouldn't be possible, right? Just to stream the data. That was the, we considered like long time and took some time to set up. And also we have like a kind of a diverse environment. So we set up different versions, different drivers. But on the C++ side, even with InfiniBand, we were still reading in parallel in Python. But once you do it in Python, you don't have actual multi-threading, right? You have multi-process, and you need to have, you don't have continuous space in memory where tasks can write. So, and we started testing, we tested multiple options, and at some point we just said, okay, let's do it in C++.
And Python is well known to not have a proper implementation of parallel processing, so you should never use it. But the one thing I was wondering about, so you are actually streaming data at high speed, and you're saying you're having a shared file system there, the seaweed thing. Is it truly that every node can see every file, or are you still loading the data in containers and only making one per container? Basically, the files available per.
No, every servers access all the files. We basically have a data storage and object storage. So, and we organize it in a collection. A collection has millions of files. Every servers can access, and we are using basically GDAL vscur. We just access with HTTP range, and we load all the data.
Interesting, thanks.
So another another question on parallel I/O, because for me parallel I/O is on MPI I/O and but you're doing MPI I/O, right? What do you call as parallel I/O? You're writing to one same file, or you like like for example with like you're writing to, for example, MPI I/O right now we do with different
yeah.
So it's not in the same sense of HPC people parallel I/O. It's yeah. So okay.
Yeah, so we write different files.
Different files, okay.
But we read from the same file. Might be the same file, because if we have like global mosaics, we just read from the same file with different nodes.
Okay. I mean, for I don't know, from my point of view, it's maybe that's not at all what you want to do. But when we want to, when we have a lot of files, because that means we will have a lot of files, right? In the end,
Yeah.
in a point of view that it's like the usage of like file system like ZA or like K-chunk, we didn't have time to explain the K-chunk, unfortunately, but it gives you one kind of global view. We can see, for example, ZA itself, you have so many small files inside, but in fact, you see just one X-array, like one data set. So I mean, how are you dealing with this? I mean, like trying to have one full view of your data set.
Yeah, basically, we made this choice basically because in the end, we are still relying in the GDAL, and our goal here in the end, it's really produce the image that I'm showing there. It's actually a single file with all the predictions for a year. So what we do is we basically, every tile that I show, it will produce 23 files, one per year, in the object storage. But with the GDAL build VRT, I basically create a VRT with all the files, and I translate and save it. But in the end, we still need to do the COG, the Cloud Optimized GeoTIFF. That's our goal here. We are evaluating doing other approach, so we could even write in ZAR, but now we are actually, what we are doing is really create separate files, and later we just merge them as a single cog.
Just for information, if you write it ZAR, you can write it separate, even with the Python, yeah.
Yeah, but I'm not sure you can also read with the GDAL, right?
I don't know about the GDAL. I don't use GDAL.
This is basically, for us, it's just an intermediate representation, right? We could still change this format, but so we can use a different format here that would be better, for example. Yeah, Antonio.
I'm in line first. Yeah. No, yeah, very interesting. And actually, my questions are more about like the modeling part. I know that that's not the topic for today, but I was very curious about some of the decisions you made there. The first one is that you said that you're predicting for the years individually. So like, and I was wondering why, like, is there an assumption that there is no cross information across the years? Why did you decide to predict the years separately?
Yeah, that's a good point. Basically, most of the land cover products, they work in a yearly base. Of course, for grassland, you can still have some transition inside of the year. For example, if you have like a transition from forest to grass, you are still mapping something that maybe to happen, I don't know, in January, right? And you kind of lose a bit the context. But what we just decided a year because it's more like how most of the land cover products are organized, and also because with the year we can have like more variables that will capture the seasonality across 1 year. So when you talk about grassland, you will have like some signal among the whole year that will be helpful to identify. And if you have a single snapshot, maybe you will not, the model will not capture it. So the assumption is you still need to have some year to capture some of the seasonality and these temporal features, instead to just classify image by image, for example. But there are products that do it. The dynamic world, for example, they classify every single Sentinel image step by step.
Right. Yeah. So that would be exactly like my next question, right? It's like if you guys were considering perhaps like using a model that can better like incorporate temporal information in that case, right? Cool. And last question, right? And perhaps that's going to be a very stupid question, but like since you're training the model in Python, if I understand it correctly, converting to C for production, right? It's like for the speed. Have you considered just doing everything in C, like since the beginning, instead of doing that?
Yeah, that's the next step that we are considering. The thing is because now, for example, even like the library that I show, it works only for random forest. But there is a nice library for machine learning in C++. We are considering use it. They even have like a Python interface.
Right.
But we should evaluate, and in this case we may move the whole thing, but that makes a lot of sense.
Thank you.
I just wanted to add to Leandro's presentation, we would like to make this data publicly available. I think it's going to make a huge difference. I think all these places where you have to go do all this cloud removal and filtering and stuff yourself is just a money making for big corporations. We are struggling where to host it, by the way. It's not easy. Many of these organizations, Copernicus Dataspace Ecosystem, lots of interest, but no action. So we're looking where to host it, but I hope October. I also talked with Wolfgang Wagner to host it in EODC, and Raymond also. I think you said possibly maybe at Surf, but we will find something. Then we will have one data cube for the world, 30 meters space-time bi-monthly. I mean, it's not perfect, but how many? It's like 600. 23 by 6, like 180 or something.
Layers, huh?
Layers, and we have also static layers and all the things. So we will make that available. We have also one data cube for Europe, which is a bit different. Then we will find the reference point data sets, land cover, JEDI, ISAT, all these really big point and vector polygon data sets. And we're going to do space-time overlay to save people time. And we're also going to release this machine learning ready data set. So you have multiple target variables, multiple covariates. For example, you have, now we estimate you have like 800 covariates from our data cube. And let's say you have 20 targets, and then you can do machine learning very quickly. Actually, you can just go with the machine learning. And also that we're going to document and release. For that also, we don't know where to reposit it. So we're looking Radiant Earth maybe. Looks like the good solution, but we would like some machine learning hub. As far as I know now, we don't have a machine learning hub, open machine learning hub. There's OpenML, but I don't know, it's a bit discontinued. So yeah, there's a lot of plans, and yeah, follow us please, and we'll be here in October. There's a conference, so we'll be releasing lots of these things, and we're very excited. We really like the talk in the morning. I think we're on the same frequency. And Pangeo, it's fantastic thing you're doing, and especially like the book you're also writing. So I think we can really learn from each other, and yeah, we'll be happy to connect. So that's just I wanted to add that things for the discussion.
May I ask? Thanks for the presentation. May I ask a bit more detail on if you did any feature selection or feature reduction when you do the random forest, and also if you did any of the hyperparameter tuning, or like how many? Like just curious about more details of like how many test runs or how many iterations you did. Thank you.
Yeah, so that's here in the top. So this part here, I'm basically calling spatial temporal model training. So the data that we have, the training data, it's a bit clustered. So we have about 7,000 regions with training data spread all over the world. We did a sampling design called feature space coverage sampling, where we kind of optimized it for climate regions. And basically we applied, so in this order, we applied first feature selection. We entered, I think, almost 200 features, and we applied this recursive feature elimination. So every iteration, we remove the 5 worst features and you will rerun it again. And the evaluation, we conducted with 5-fold spatial cross-validation. Here, the spatial cross-validation makes a lot of difference, because for every region, we have points that are pretty close. And if you don't remove all the points for that region, the model evaluation will be biased. So we used this spatial cross-validation. We selected the features, and I used this successive halving. It's also implemented in scikit-learn. So basically, you start with several parameters, and you reduce the number of parameters, select the best hyperparameters, and reduce also the number of training points. And in the end, we do the comparison with random forest, gradient descendant tree, and artificial neural network. And everything that we did, it was considering log loss, because we were interested in predict the probabilities, and log loss it's more suitable for probabilities. Yeah.
So just a quick question. So the Landsat, I saw some, so we are from ocean, so we don't care about land data, but my question is like, I saw some people treating Landsat data for sea surface temperature, or so there are some, so there are some area, I guess, that people have the information. I'm sorry, I'm from model people, so I really don't know about satellite stuff. So can you please explain it, so that it's the satellite itself only really measures on the ground, on the land, or you also, because I saw your patches, it's only on the ground, right?
No, yeah, but the Landsat data you have, to be honest, I'm not sure if you have, maybe you have some really raw products in ocean. The question is if the Landsat data, it's also covering ocean waters, right?
Yeah, and then so you for in your study, basically that your original data that you use have data on the ocean, but ocean part you throw it away.
Yeah,
Okay.
but it's in the more in the coastal area, not all the ocean. Even because this is also, it's a kind of post-processed product. So, but even USGIS, I think they don't release, like, I'm not sure actually, but Landsat for like ready to use for all the ocean waters. You need to go for kind of more raw images. Okay.
Thank you for a nice talk. My question is first about have you done any evaluation about the feature importance, which feature was like more formative for your classification? And second is about the accuracy assessment. How you did the validation of this product?
Yeah, so we did the feature importance. So we just retrieved the most important features for the random forest. And for example, for the natural and semi-natural grassland, the features about the accessibility maps, they were very important. And this is something that I still need to check, because the accessibility map it's quite coarse. It's 1 kilometer. So the map, it's basically producing like areas, like these areas, like areas where more isolated, then it's classified. It makes sense, but the problem is the most part of the decision it's taken using these variables. So some areas that are natural, but like national parks and things like that, they are not captured, for example, in the current version. So and also it's a bit risky when you have like several coarse variables that dominating the feature importance, because basically the signal of the 30 meter here, it's kind of smoothing out. So that's one concern. And the accuracy assessment, what we did, it was cross validation also também, but 5 times spatial cross validation. So it literally is, you remove 20% of the data and you train with 80, right? And you do it 5 times to iterate over the whole data set. So, but we want to conduct independent validation assessment, and IASA group, it's working on that. So in this way, they will put more points, do the evaluation. So, but for now, we just have this cross validation.
If I may, just to clarify, because now I'm a little confused. So the trainings is still done in Python, or is also C?
In Python.
I'd assume that the most costing part is actually the training rather than the inference. So it's
no, the inference here, it's way more costly, because it's the number of data, it's way more. For example, the training part, we use 2.3 million points. And this is just this is less than 1 tile, right, that I presented here. And we have like a lot of, this is, it's a kind of the other way around. But we did the training in Python, even this hyperparameter, everything, it took in one server about 10 hours.
Okay.
Exploring all the threads and things like that, right? Hyperparameter.
So in terms of like amount of data, like in percentage wise, how much of the data is actually being used to train these models?
Yeah, that's a good question. So if
I think my question is like the way how you're selecting the training samples, right, to fit the model. Like, how do we ensure that it's representing the distribution of the whole data set?
yeah, for that we developed like a different. We have a kind of a sampling design. I can briefly show to you. That's a good point because the thing is we have, as you noted, the amount of data that we need to predict it's like massively more than what we want to train. But here we really need to produce training data by ourselves, right? Because there's no training data that classifies pastures for us. So there's like a huge presentation here that I can try to open just a second, and I can show the how the training data looks like. But basically, we did this. We worked at 1 kilometer and we selected the most interesting areas for to run the training to just to put points and just conduct the visual interpretation. So I'm not sure if I will find it now, but at least the training points I can show to you.
We can also discuss that later. I don't want to take all your time.
No, I think this, yeah, this is actually what I removed, but it's global coverage, but I can briefly explaining how I did this here. I think here I can show that's the thing. So that's the training data. Mm-hmm. So for here we selected about 10,000 points, and these points they represent 1 by 1 kilometer area. And for each point, it was conducted a kind of a visual interpretation where the interpret literally selected, here is grassland like a polygon. Mm-hmm. We did that with a QuantGIS plugin, but I derived points equally distributed, so every 60 meter to match with the Landsat data. So that's actually how the training data looks like. For every point, we have that amount of data. But even so, it's comparable to the whole archive. We might miss some areas. But what we did here, we conducted they call like feature space coverage. So we got like vegetation indices, some temperature data, and we put everything together and we run a PCA. We throw away some of the components and we end up with 10 components, 80% of the variance, and we run a k-means with 10,000 clusters. And once you do it, you do an unsupervised classification, and for every cluster, we took the center pixel of the cluster. And in this way, we guarantee the maximum variance, the variability, and we just interpret it. But of course, this was in a 1 kilometer data, so it was not in the Landsat, but it kind of represent kind of some of the spatial and nature patterns.
Thank you.
Yeah, thank you, Milutin. And yeah, that's we only have the last survivors here. So I will, basically, Milutin asked me to organize this discussion. And as he said, we had this idea to kind of use what we learned here to kind of write a white paper, can be even like a technical note or something like that. So the idea is, so what I will show here, it's basically a few slides trying to really explain where you can implement your big data problem, right? And maybe some of you, it's not really a big data problem. You can work in a local environment, that's also fine, but you can still do some of the decisions that I will show here. And in the end, we can brainstorm about what could be the problem and the application that we could tackle in this white paper. And everyone that joined to the hackathon, of course, it's welcome to contribute with this white paper. So yeah, that's the idea. So where to implement my big data problem? So we have all these platforms, and we learned today about the PanGeo, and it's running this EOSC. Of course, everyone knows about Google Earth Engine. We talked a lot about the Copernicus data space ecosystem. Use a bit of this, a lot actually, the surf. But you have also like some applications, some data. It's in the Sentinel Hub. OpenGeoHub has also data. It's part of the Copernicus data space ecosystem. So it's really difficult to really go for like a platform and just make a decision, right? To keep working. So what I try to do here, it's basically guide you with 4 questions. So the first question, it's basically, if you are working with Earth observation data, you need to think where this data is, right? So which will be your Earth observation data provider? So if you are working with Sentinel-2, where you can find Sentinel-2 images. If you are working with Landsat, for example, we saw this foundation model, the HLS, where the HLS is, harmonized and Landsat Sentinel. So basically here I put different platforms. Of course, some of these platforms, they are both. They are the Earth observation data provider and also computing platforms and things like that. But some of them are really just the data. So for example, if you go to Amazon Open Data, they have the archive of Sentinel, Landsat, and it's just everything there as object storage you can easily access. Or you can go, for example, to some USGIS website and just download it. More recently, I discovered about this Google Earth Engine high volume endpoint. So I put this presentation in the Discord so you can have access to all the links. So for example, this Google Earth Engine high volume endpoint, it's a way to really transfer data in an efficient way, stream data directly from Google Earth Engine for other platforms. So in the Open Earth Monitor, we have like a partner from WUR that it's doing it to use like a CEPAL platform. So to, for example, predict with Planet data. So yeah, you have different options: Microsoft Planetary Computing, Sentinel Hub. But of course, the main point is which data you want to use and where this data is hosted. For example, the data that I show in my last presentation, the Landsat R&D, it's not available in any of these platforms because this is only available in the data center of the University of Maryland. So in this case, we literally asked them to copy all the data to 20 terabytes hard drives and ship it through the ocean. So, and basically we received the data like that. So like, I don't know, 3 or 4 batches of hard drives, and we copy it to our system. But of course, this is a specific use case, right? It's just an example that you are constrained, of course, by the data that you are using. Another decision is which computing infrastructure, right? And here, computing infrastructure, I basically mixing the 2 concepts that we saw with PanGeo colleagues. It's basically scaling computing and resource management. So which solution you use to do these 2 tasks for you. Of course, if you are working with your notebook, you just download the data for a hard drive and you can do. But if you want to really scale up, it's a bit difficult to do it. So you can use the Copernicus data space ecosystem, different platforms that we see there, that we saw there, Surf, right? We use it. The EOSC, yeah. From that we see this morning with PanGeo. You also have OpenGeoHub, and if you want to use OpenGeoHub, Patrick also said about this NOR sponsorship, so you can ask more credits to really scale up your computing. Of course, Google Earth Engine, it's also a solution. Planetary Computing Hub. We didn't discuss about, but this CPAL, it's also a platform that it's close to Google Earth Engine. I think they run in the Google servers, and it's supported by FAO. You can also use. And you can also go for commercial clouds, right? So if you have the data in the AWS, you can just hire like a machine in the AWS and just have high access. Of course, you need to pay for that, but that's also a possibility. Or you can go for an in-house computing center. That's what we did basically.
Sepal is actually on Amazon.
Amazon. Okay. That's a good information because when I think from VUR, our colleagues, they use it and it was quite okay to stream data from Google Earth Engine. So it's good to know about it. So yeah, that's a kind of the second decision. And of course, which processing library softwares you want to use, right? You want to connect it. So we saw several options here, PyGeo, GrassGIS, of course, GDAL, several machine learning. So this is more like about, which software are you use, with programming language. And more recently, we can also, if you want to use a foundation model, which foundation model you want to use, right? We see the Prithvi, maybe it's not the right way to say, but the foundation model that we see with Antonio. And basically, but there is also this Clay foundation model. And when I started putting some foundation model examples here, I thought, okay, maybe there is not such much. But if you enter in this GitHub, you can see dozens of foundation model for Earth observation data. So it's a quite hot topic. But specifically for what we saw in this week, like that Antonio presented, it's basically we have the HLS data, right? So, and that's a good example because this foundation model was trained with HLS data. So that's a hard constraint where we have HLS data in all these options that I showed you. And it's basically in 3 places. So you have in the USGIS, so you can go there and download it. If you really try to do it in a massive way to download, they will block you. So you cannot really move the data easily if you want to, for example, predict and download the whole Europe, right? So you can go to Amazon. They have a close connection with the USGIS, so you can also stream data to there. That's an option. You can go to Google Earth Engine. It's there. And it's also in Sentinel Hub. That it's not irony, right? Now Sentinel Hub, it's owned by Planet Labs. So basically it's only in the US, American platforms, if you think about it now. But the thing is, so if we want to use this model, we need to rely in some of these platforms to really access the data. Okay, so if you think about it, let's think that we want to develop like an application that will be based in this foundation model, and we can test as we saw in the presentation. We can test like even like a machine learning model, like a random forest or a regression model in the end, and just plug it. But we still need to stream all the data. So, and we have some decisions, right? So if we have this big data problem, we can be a land cover mapping, can be some other regression type. We need to define which platform we want to use. And here I put just a few options. We don't need to stick with that. But the interesting part is if we select one of these platforms, of course, there will be implications of how we will move the data around, right? So if we want to use the SURF to run this foundation model and implement our big data problem, SURF has no access to this data. So we need to find a way to first prepare the data there, right? Or if you want to use Google Earth Engine, the data is already there. Okay, but once we run it, you cannot run this foundation model directly in the Google Earth Engine. So you need to run in a Google compute engine, like a kind of a VM, and stream the data. So all these decisions, of course, it creates different pipelines and different complexities. If you want to run in the Copernicus data space ecosystem, it's fine, but how we will access the Sentinel Hub there, right? So if we could use, here it's also included the OpenGeo, so OpenGeo would have access to a collection that it's actually in the Sentinel Hub. All these things we still need to decide and see how it will perform. So the idea here, it's actually, for now, it's really, we could brainstorm and think what would be a nice problem. Could be some land cover map, could be even this grassland map that I show, I have training data, but it needs to be some application where we can really train a supervised machine learning model on top of the foundation model. And that would be an interest application. And as use case, we could implement exactly the same application in at least 3 platforms. And if we do it, and of course, we need to scale it a bit, not the whole world, of course, but to be honest, it would be great if we could run at least 1 year, whole Europe, because that's actually a massive amount of data. We could run it in these 3 platforms. And if we do it, so we will kind of understand these complexities and we could document it and create a guideline, right? So if you really want to scale up in surf using some data that it's not in their infrastructure, what we need to do. So if you want to run it in the Copernicus, what are the limitations? You really need to put your credit card and scale up, and what will be the cost? So they can predict that and things like that. Or if we want to use this EOSC, right? Is it possible or no? And things like that. So that's mostly the idea that I was discussing with Milutin. And as last slide, I just tried to put here this kind of simplified architecture. And mostly that's the way that I see. So when we talk about this really scaling up, we could have some monolithic solution that I'm showing there. And even for this monolithic solution, it means that you have data provider, compute infrastructure, libraries, and even like some foundation model in the same location, right? It's in the same infrastructure. That's just communicating locally. This is something that, for example, I show in our example for the OpenGeoHub, the grassland map, but I still need to copy the data. But this is something that I do in advance, right? So, for example, if we rely in surf could be a kind of a monolithic solution, but we still need to move data to there. Or if I rely in Google Earth Engine, it's also a kind of a monolithic solution on the perspective of the user, right? The user doesn't need to organize all these kind of communication protocols and things like that. When we talk about federated, everyone talks about federated, but to be honest, I don't see it happens in practice, right? When you talk about federated, it's basically you need instead to copy this data around, so you can't just move the whole Sentinel collection from one side to another side, right? So you need to effectively define these interoperable communications and split the pipeline and the workflow in different locations and different computing infrastructure. So these federated systems, okay, it's something that we should invest in, and that should be the future. But how effectively we can implement that, right? So we need to rely still in massive infrastructure to move this data around. So, for example, Surf could have a directly access, I don't know, to Cloudflare or the other place where we have like Sentinel data. How it would work? So instead to copy the data, they could access there. But so this federated solution, it's something that we could still discuss also in this white paper. And just provide like some of concrete limitations, right? When you really want to use it and scale up your computation, what are the problems that you come up basically? So yeah, basically that's kind of overview of this idea, and we have a nice opportunity to really contribute with all these platforms as a kind of a concrete application. Yeah, that's all from my side, and now I can open to discussions and questions and feedback.
Yeah, thanks, Leandro. I think that's basically the idea we want to do now. So maybe I don't know, shall we stick to this slide or maybe open another slide and then just start collecting like brainstorming on those things. So what do you see where? So for example, which EO data provider you are working in, or like how we can implement this in PanGeo, or yeah. What do you think about that? So
Yeah, I think the first point is because you said about this foundation model, right? If we stick with that, I think it's a nice idea. So we should, if the first decision is, are we using a foundation model or not? I think we should think about it, because if we use, we have the first constraint that which is the input images, right? So if we use HL, we could just stick with that, as I said here, and okay, so it limits where the HLS are.
No, that's easy. Are we using foundation model or not, or just simple machine learning? So what are you more interested in? So generally, so after the whole week, so which workflow would you like to have? That we brainstorm now about foundation model that is adopted to some particular application, or you just immediately want some simple machine learning model? Okay, so who is for foundation model? Yeah.
Can we have both?
Can we have both? Yeah, let's, depending on the time, like I don't want to torture you. Yeah, but but I think foundation model is a more complex workflow. Yeah.
Yeah, I think that the question that needs to be made is first, right? Like, as Leandro was saying, what's the nature of the data that you're going to be working with, right? And that's what's going to dictate what's the actual machine learning framework that you should be using, right? And in that front, right? So like, if your data has some component to it that fits within the expected input format that PreTV or like other foundation model is using, then by all means, you should take advantage of that, because it's a model that has been exposed to like really large data sets. So like, there is only benefits that should come from that. If you have extra data, which like some of the people here do have, right? You can have another component to your neuronal network that's going to handle that jointly with the foundation model, right? So like, but again, the decision in terms of like the machine learning infrastructure that you're going to be using is very much conditioned to like what's the nature of the data that you have. So like, just to summarize, should you use a simple CNN for your case? Maybe, but like how much data you have as well, right? So like if you have just a couple of hundreds of samples, you're very constrained in terms of like architectures you could potentially be playing with, which I think it's like the majority of the people.
Yeah. Okay. Yeah. No, that's a good thing, but that's the whole point of this session. So we should just brainstorm and try to find the best way. I think we use data cube. So from my point of view, my requirement is a data cube. Which data cube? I personally don't care. And so we need application as well. So which data we use, then we have another question, which application at the end. So what's our goal, final goal? I would say I also don't care much about the application, but so for me, like some framework is a data cube, and we can do classification problem, yeah? So it can be, we can do the mapping, pasture mapping, or we have a lot of in situ data. YASA has some data. We can also brainstorm. So if anybody, so the idea is at the end when we brainstorm about this workflow, we then try it, like try to implement and then assemble this white paper all together. Yeah. So maybe later. So we don't try it today. Don't worry. So it's just the brainstorming. Yeah, but we try together later before we made this, we published this white paper. So I think this I remember you said, Leandro, you had some data for pasture mapping. What do you think about this application? Or
yeah, we can do, because as Antonio was explaining, so for the data for pasture that we have, the grasslands, we have kind of really polygons, because the analysts, they literally kind of delineate regions at 10 meter of kind of raster format, but the delineated regions that it's kind of a suitable input for semantic segmentation, like UNet and things like that, but it's only about 7,000. So, and what I did in the grassland mapping that I show, I used these regions to put points, right? So one way to explore it, it's use the foundation model, but work with the complete polygon delineation of the samples. So, and if we do it, we could still compare with the pasture map that was produced with random forest. And of course, it run in a different infrastructure, but also it's compatible with the resolution because the HLS, it's also like 30 meters. So we could, what I'm trying to say is if we do this pasture map like that and we define, we can test the foundation model and we can compare the results with the baseline. That it's basically what I presented in the last, in my last presentation.
I'm just trying to make notes. So
yeah. So this is one way to go. So I think we if we just stick with that, independent of the problem, we need to find ways to implement it in these different platforms. So we could, and to be honest, I think we should have at least 3 platforms because it will give us an overview of the limitations. But this is also complex, right? I don't know, for example, if we want to, that's the thing that we always ask for when we see these platforms, right? If we want to really scale up this processing, now we want to do the whole Europe 1 year and apply the prediction, for example, as I show, but like only for 1 year, we want to do it in the Copernicus data space because how it works. We need to pay like in advance, we put a credit card. So because I know how it works in commercial clouds, but in these platforms that abstract it, I don't know exactly. So with Surf, I kind of understand how it would be. We literally need to move the data to there, right?
Yes, I mean, we can also get the support from network of resources, I think also for Copernicus data space ecosystem. So I guess, yeah, so I have to talk with Patrick, but I think we can maybe ask, apply for some credits there, and we can, theoretically, we can do it there, yeah.
Okay, I think that's actually, it fits perfect for the project.
Technically, for one thing, I have already applied on the project level. And second, it is a different stream from what ESA does. So the network of resources doesn't actually apply to CDSE, but they have their own support channels, basically.
I have one email. I have to check it. So because I think he mentioned that they have also, they support this. So just to double check.
Yes, maybe we can get some extra this, but then I think it would be actually good to sort of lay out what the implication would have been for any user. So the right for the paper sort of take the stance of like a neutral, non-well connected user that just tries to find his way through the computing services that opens the data spaces.
Yeah, you mean like we want to write something that is, of course, it's generic and kind of a guideline. But for me, to be honest, the way to understand this limitation is really trying because all this, even for example, the Copernicus data space ecosystem is quite new, right? And to be honest, I don't see like some applications they scale up, but for me it's not clear. So what I'm trying to say is if we just have like application, of course, it's just like a use case. What we want to emphasize is all the limitations and how like a user that it's not doing grassland mapping would use the Copernicus data space ecosystem or Surf to really run, I don't know, continental computational, right? But that's a good point. So let me just show the data that we first grid inspection. So we developed this plugin to QuantGIS. Let me see. Yeah, this one. So, and basically that's how the analysts, they labeled the regions that we have. So, and it was about 15 people, and we developed this plugin. So they are checking, for example, a region, and they selected which class here. So here's seeded grass. We call now a cultivated grassland. And they have this grid with the, it's a grid, but it's 10 meter. So it works as a raster data, but it's actually like a vector file. In the end, it will be a geo package. But doing like that, you have like the advantage to use this multi-edit functionality of the QuantGIS. So they literally select all that regions, and they say, yeah, all these kind of 10 meter grids cells, they are classified as seeded grass. So we started developing this plugin specifically for the Global Pasture Watch. And in the end, I said, this is really useful. And I talked with the main developer. He's based in Brazil at University of Goiás. And basically, he customized the plugin. So, for example, if you download, you have an example campaign that you can do with this class, but maybe you are not interested in grassland. So you only need to edit a JSON file, and you say, I'm interested in agriculture, or I don't know, some water analysis and things like that. And the layer that it's in the back, it's basically Google Maps and Bing. So this data was labeled considering Google and Bing Maps. And for the Bing Maps, you can retrieve the date of the image, because of course we need to find the date. So you can retrieve the date of the image by API. He implemented it. But for the Google, they don't have API. So you need to go to the Google Earth Engine, Google Earth, not Earth Engine, the Google Earth, to see what is the date of the image, and you put here. But we created all this workflow kind of organized in the platform. So so that's the nature of the data that we have. And for example, with this data, we could really train a kind of a model based in this foundation model to explore the possibility. And that's also a nice application, because one thing it's just do pixel prediction with classical machine learning. Another thing it's when you really need to do some inference with deep learning algorithms.
I just found the email, so it I think it's possible to get a virtual machine on CDSE. Yeah. So so through NOR, yeah. So access to virtual to VM there, yeah, and probably data, yeah. So
yeah, if we have a VM there, we yeah. This thing I also don't know, because the data it's actually in the Sentinel hub, right? But yeah, we probably not sorted out all these problems now. But I think, to be honest, that's a nice use case, because HLS it's cutting edge data, right? It's Landsat and Sentinel.
That's perhaps more of a question to Milutin, since he's taking a look at the resource. Would these VMs have access to GPUs as well? Because that's also deterministic on what type of models you can use, right? So, for example, PreTV, if you're going to train that in CPU, is not viable, basically. So,
no idea. But we have to explore, yeah.
But about it, could we use just the pre-trained algorithm without any fine-tuning or transfer learning, and just use that to produce a compressed representation, and from this use, I don't know, some machine learning random forest, right? That would be possible?
Yeah, absolutely.
Only with the encoder part.
Yeah,
right?
yeah. You just use that as a compressor, essentially, right? So you can encode your tiles to these latent representations, which should be meaningful, since these models have learned how to extract features from the image in a meaningful way. So yeah.
And do you know the size of the latent representation, kind of roughly?
Yeah, it's usually it's going to be a vector. Let's say that you have an image that's 224 by 224 pixels. If you're using the default settings, the pad size is about 16. So if you do 224 divided by 16, that should be 14. 14 squared, that's 496. So like it would be a vector of 496 by
Okay.
768. Yeah.
Yeah, this is doable. Yeah.
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 I just have the idea or maybe question about, like, I think all of the researcher or everyone here they're familiar with the tool they are using, and now we come to talk about how to do thing on the cloud, and we move things to the cloud and compute layer, and sometimes we trap the different platform, and this works for some cases, and this works for another cases. For example, the PanGeo and the OpenGeo and Surf, they all developed their own package or like functionality. I just wonder how easy for a user that they got used to one platform, but they found out the limitation, and how easy they can just move to another platform and try it out, how long it takes, and is it doable to reduce the barrier between platform that everyone just have the common knowledge, they can just move their code and try to modify it according to the different platform setup? It can be improved, or how can you build the...
Yeah, that's a good point, and I think we should kind of address it in this white paper. The way that I see is I didn't put, but there is also like kind of a decision that you need to take. It's basically what the development environment you are using, right? So most of what we did here, it was in the Jupyter Lab. And in the end, for example, we managed to instantiate the Jupyter Lab in the Surf infrastructure, right? And we saw that you have desk and desk access the nodes, but in the end, it's still a Jupyter Lab that you could run in your own computer. So we also have Jupyter Lab in the Copernicus, and we also have, so the thing is, of course, you are quite flexible with Jupyter Lab, you have different kernels, but that's a kind of a common denominator if you think about at least 3 platforms that we are seeing here. In the Google Earth Engine, it's completely different, right? So you can do some stuff actually with Jupyter Lab, but you can access remotely, you have the Python environment and things like that. But it's still a bit different because all the backend, it's kind of there, and you can have the Jupyter Lab running, for example, in Colab or things like that. So, but for example, if you talk with people that use R, they are maybe more familiar with RStudio. So for sure, you could also have like a R environment maybe running in Surf and things like that. So I think what we could do, it's basically explain how you can first instantiate this different Jupyter Lab instance. So what are the difference among this process? But once you do it, it should be pretty straightforward. You can, of course, some libraries will be missing. You might miss some kernel, something in the environment you need to install and things like that. But you should be able to do the processing. But still, this is just like maybe for prototyping. The second step, it's how you really scale up, right? And maybe for scale up, that's a different thing. So you still can have a Jupyter Lab running in all this platform, but the way that to send it to compute and distribute the processing part, you can do it with Desk, or you can do it as we saw with Giuseppe, like really creating the tiles and send it to Slurm. So, but this thing we also need to discuss, right? The thing is, if you have a solution that does it for you, yeah, that's more easy to go, but it's also less flexible, I would say.
Yeah, I'd have more of a question as well. How would it be possible to, especially with consideration of the Prithvi model, include image data from different satellites of different resolution, or from Landsat and Sentinel satellites at a lower resolution of like 10 meters? Are there workflows to use it and to use the Prithvi model maybe as a pre-processing on a rougher resolution and then do a hierarchical approach? Are there workflows implemented for this? Is this a consideration, or is this just a complete folly? Do you maybe know something about this? Anyone?
Yeah, that's a good point. So I think Antonio can say more about it.
No, yeah. In fact, like some of the colleagues here, they are working on perhaps how to adapt this framework. And Leonardo can give more details later because she's actively working on that, right? No, no, but yeah, there are ways how you can integrate other layers. So like if you have other sources that are not just sticking to like the 6 bands that we discussed, right, during the lecture, you can use a CNN that's going to be trained jointly, right, with this model. So like in this case, you'd have to fine tune, right? Like a model that can leverage these extra layers that were not included in the initial pre-training, right? Another alternative would be to train a model or like use a more simplistic way just to encode that to a latent representation, right? Which is like what you're saying here, even skipping completely the fine tuning. So like just bring it down to the same level of dimensionality. And then you have one layer. So like one simple thing that's just combining what's coming from output of the encoder of PreTV with the latent representation that's being delivered to you using a second software that's coming separately. So there are ways to do that. In the ideal world, fine tuning is always better, right? As long as you have resources to do so.
Yeah, and the way that I see it's this HLS, it's really a well done product, right? So if you are sticking with like multispectral imaging, it should be enough just have, because it's really harmonized Landsat 8, 9, Sentinel-2, right? But maybe you want to combine some Sentinel-1 that can add a bit more information or some static layer. So you could do some fine tuning, right? Or also one thing that would be possible, you can also do a fine tuning for specifically for your problem, right? So we could have like some areas where we know that there is grassland and we could fine tune the model to really focus in features that we know previous that there grassland there. So it can learn this specific domain because there is no specific, I think they did for land cover in general, but you can still specialize it for other applications, the fine tuning. So, but of course it costs resource. So you need to balance.
Right. In the question of the resources, right, Richard, is very significant for us here since you're like mostly doing open source work and with like very limited resource. One of the key benefits, right, of foundation models is that you don't need to have like really large data sets for the fine tuning step. You can fine tune a model with like really small data sets. So like we're talking about hundreds, no longer like thousands, right? So like even if it's expensive from the point of view of resource, right? It's gonna take a while, but it's doable. So like you're not gonna spend like 40 days waiting for a model that's like doing poorly. That's what.
Great. Okay. Any other question, feedback? Yeah, I think everyone is a bit tired, overloaded, and
Yes, yeah, I think we put this session a bit, mistakenly at the end. So we should put it a bit earlier, but it's difficult. And I would also like we finish earlier, because then like staying 1 more hour doesn't bring much. So if there are no other questions, so I would say maybe Leandro, you can explain how people can engage with this work. So who would like to engage to this white paper, and shall we? I don't know. Continue on Discord.
Yeah, I think the next step it's mostly we need to we kind of define the problem, and we need to sit and kind of plan what will be the pipeline and how we will test it. And I can basically send an email for everyone. We can talk also in the Discord, but maybe we should have like a follow-up meeting with people that are really interested. So I just send the invitation for everyone, and in this follow-up meeting, I basically present a kind of a plan, right? So because part of the work, it's really testing these platforms, and part of the work is write the lessons learned and things like that. So we should have a follow-up meeting maximum 2 weeks, I would say.
Yeah, so this sounds good. I mean, the follow-up meeting, yeah, before everybody goes to the summer break, that's yeah, that would be good.
And we just in this meeting we just present some of the definitions, right? We should know how we will run it in the Copernicus. We could talk with Raymond if we could have a copy of HLS for 1 year in Surf and things like that. So, and we need to do it in advance and just present what will be the general framework, basically.
Yeah, yeah. Good. Yeah. So then I think that's it. Yeah. So then we continue on this follow-up meeting. Yeah. Okay. Good. So. And please don't be shy. So just just engage to this communication and join the meetings. And if you think you can contribute to testing, let us know, and we would be happy for any kind of help. Yeah, and yeah, and at the end we can write together this kind of white paper, or yeah, we will see what it will be. Maybe a paper. Just a paper, or yeah. Okay. Good. Thanks a lot. With this, I will conclude the hackathon. Thank you very much for visiting YASA, for participating, actively participating. Thank you also for doing the measurements with the mobile app, and yeah, congratulations to the winners, to our best data collectors, yeah, who really understood the app in such a short time. Yeah, and I hope maybe next years we will find some funding to repeat this event, in one or another form. Yeah. So thanks a lot, and have a nice trip. Nice and safe trip back home. And yeah, we go to Vienna now, yeah, probably in half an hour, like 15-20 minutes for some drinks spontaneously. So if you like, please join us. Yeah, thanks a lot. Yeah, welcome.